Hey everyone, this video is on molecular shapes and geometry and VSEPR theory. VSEPR or VSEPR theory stands for valence shell electron pair repulsion theory. This is a very commonly used to predict the three-dimensional shape of a molecule. Now, as we delve into the specifics of the structure of molecules, we need to be aware that most of the time when we're drawing a molecule, such as methane, where a carbon atom is connected to 4 hydrogens, we often neglect and forget about that these molecules often have a three-dimensional shape, and they're not simply a two-dimensional structure on a piece of paper. So in this case, as an example, methane actually adopts what we call a tetrahedral shape or structure about the carbon atom, where the hydrogen atoms are extended in the 4 vertices of a pyramid, as you can see here. This is called tetrahedral, and the angle between the carbon and hydrogen is precisely predicted to be 109.5 degrees. In the VSEPR theory, there's one important assumption that we always use, and that is electrons, whether they are bonding in covalent bonds or non-bonding as electron lone pairs, will always repel each other due to their negative charge. And this repulsion will cause them to move away from each other such that they will try to maximize the distance from each other. And when distance is maximized, the repulsive force between these electrons is also minimized. This is why in this particular structure for methane, you see that the bonds between the carbons and the hydrogens are spread apart so that they are evenly spaced away from each other to achieve this minimal repulsion. The exact shape or geometry predicted by the VSEPR theory depends on the number of bonds that the atom is connected to, as well as the number of lone pairs, and these are referred to as non-bonding electrons. In the textbook or online, you will often come across a table that tells you the different types of geometry according to the VSEPR theory. On the column of this particular table, we have the total number of electron groups. Electron groups refers to the bonds as well as the electron lone pairs, as we previously mentioned. Across the rows, we have different numbers of lone pairs that the atom has. So for example, if a molecule has a total of 2 electron groups but 0 lone pairs, it will adopt a linear shape or geometry. Let's go through each of these using some common examples. Beryllium hydride consists of a beryllium atom and 2 hydrogen atoms. Because the hydrogen atom only has 1 electron, it cannot be the central atom, so the beryllium atom will be surrounded by the 2 neighboring hydrogens. The shape around the beryllium atom can be predicted by considering the number of electron groups it has, precisely how many bonds it has, and also how many electron lone pairs it has. Beryllium is in group 2, so it has 2 valence electrons. By forming the 2 covalent bonds, it has already exhausted all of its electrons, so it has no non-bonding electrons. So the bonding groups will be 2, and the lone pairs will be 0. By referring to this table here, we can see that this will adopt a linear structure. In the linear structure, the angle between the bonds will be exactly 180 degrees. Carbon dioxide also adopts a linear structure, even though it has double bonds. Around the carbon atom has 4 bonds, but this is actually considered as only 2 bonding groups. Each double bond between the carbon and oxygen atom is considered as one bonding group. So the bonding group is how many groups of bonds the atom has. So one double bond will be considered as one bonding group. Carbon is in group 14, so it has 4 valence electrons. And by having these 4 bonds, it has exhausted all of its valence electrons, so it has no lone pairs left. So this, by using the table, tells us that in carbon dioxide, we'll also have a linear shape where the 2 sets of double bonds will be 180 degrees apart. Next we have boron trifluoride. Boron is an element in group 13, so it has 3 valence electrons. In this case, it has used the 3 valence electrons to form the 3 covalent bonds with the 3 fluorine atoms. So it has 3 bonding groups referring to the 3 single bonds, and it has non-bonding electrons. The geometry around the boron atom can be identified by using the table once again. So we have exactly 3 bonding groups and 0 lone pairs. And this gives us a geometry called trigonal-planar. Trigonal means the bonds are spread apart in 3 different directions. Planar refers to the fact that the 3 bonds are in one plane. They are 2-dimensional. This also will help us understand that the exact angle between the three bonds will add up to 360 degrees. So if we divide 360 by 3, we'll be able to obtain the angle between the two adjacent bonds, which is 120 degrees in a trigonal planar geometry. In the water molecule, an oxygen atom is bonded to the two hydrogen atoms via single bonds, so we have two bonding groups. Since oxygen atom has 6 valence electrons, this will leave 4 non-bonding electrons as 2 lone pairs. So we have 4 total electron groups, so 2 bonds and 2 lone pairs, and 2 lone pairs out of the 4, bent or angular structure. You can understand this as if the 2 electrons pairs are repelling each other and also repelling the covalent bonds away. This is why water doesn't exist as a linear structure, but a bent one, because the bonds are being repelled away from the electron lone pairs. In methane, as we discussed in the beginning of the video, the carbon atom is attached to 4 hydrogen atoms via single bonds, and the carbon atom does not have any lone pairs. So we have 4 bonding groups as 4 single bonds and 0 lone pairs. In the table, this identifies as a tetrahedral structure. In a tetrahedral structure, the angle between adjacent bonds is not 90 degrees because they are not in the same plane. This is actually 109.5 degrees. When in this geometry, the bonds will maximize the distance away from each other and also minimize the repulsive force between the electrons in the bonds. Remember, this is always the assumption behind using the VSEPR theory to identify the most optimal geometry about an atom. In the ammonia molecule, we have a nitrogen atom connected to 3 hydrogens. Since nitrogen is in group 15, it has 5 valence electrons. If it uses 3 electrons to form the 3 covalent bonds, it will have 2 left over as a lone pair. So we have 3 bonding groups and 1 lone pair around the nitrogen atom. In the table, this will give us the shape known as trigonal pyramidal. This is different to trigonal planar, because the 3 bonds are being pushed away from the lone pair due to repulsion, so they no longer exist in a plane or 2-dimensional plane. They are now extending downward away from the lone pair. It's called trigonal pyramidal because you can actually join the hydrogen atoms together to form a shape that looks like a triangular pyramid, hence the term trigonal pyramidal. In phosphorus pentachloride, we have a phosphorus atom connected to 5 chlorine atoms. Phosphorus is in group 15, so it has 5 valence electrons. And all 5 valence electrons are being used to form the covalent bond. So again, the phosphate does not have any lone pairs. It has 5 bonding groups as 5 single bonds and 0 lone pairs. In the table, this will help us identify that the shape of this phosphate atom will be trigonal bipyramidal. The reason why it is called trigonal bipyramidal is because we can create one triangular pyramid like this above the phosphorus and another one below the phosphorus like this by connecting the chlorine atoms as I'm drawing here. So you've got one triangular pyramid at the top and one triangular pyramid at the bottom. Trigonal bipyramidal. This concludes the video on VSEPR theory and molecular geometry. Hey everyone, if you found this video helpful, smash that like button and don't forget to subscribe. Want even more? Become a Patreon member for early access to videos, exclusive Discord discussions about questions on chemistry and physics, and live preparation sessions for your exams. Don't forget to head over to our website for topic tests and practice exams to further improve your understanding and learning.